I will be starting in less than 2 minutes. Hello and welcome to Microcontrollers with kingernorth. I'm your host, kingernorth. This is episode 21, track level indicator with CircuitPython and Arduino. So let's get started. Here we go. Let's have a look at what we're going to be using today. So today I've got here a few items on display. And what we're going to have here is we have our typical Arduino here, and that's the one that's connected right now and running. It has 3 indicator lights, which I will talk about. We're also using an accelerator, which I will also be talking about. It's an acceleration board, and it measures acceleration in six different directions. And then I have the Feather M4 Express from Adafruit that I'll be running as well to run CircuitPython code on. And with that, I'm also going to show you a little trick on how to calibrate this. We're going to give it a try and see if it works well. So I'm going to show you a little extra programming with that, which you can apply the same principles to the Arduino program. This whole thing could be done if you want, instead of using one of these larger boards, this is that little tiny board, that trinket that I used before, that programs in both Arduino and in CircuitPython. I know for sure in CircuitPython there'd be enough room, but you could actually build this whole circuit with that and not have a problem with it, and it would have plenty of room to do it. It would probably work for the Arduino version as well. I'm not sure about that. I'm not sure how much room the libraries take up, but I think it'd be fine. Also in here is the Circuit Playground Express from Adafruit. This is an all-in-one board. This thing has a pile of sensors in it, as well as a built-in accelerometer. So on this board, in a location somewhere on here, marked with the X and Y. Let's see if I can find it. Oh, it's right in the middle of the board. It's a tiny little chip right in the middle of the board. And you could actually use this and use the lights on it to do the indications. So you could have an all-in-one board solution. The only thing you'd have to hook up to it is power. And you could do that with a couple of 2 or 3 AA's. 3 AA's work really good. You don't want more than that. In fact, I think actually it works well with 2. I would have to go back. You can use AA's as well. So you can actually build a level indicator with this without an external sensor. This actually has a sensor built in on board. And again, this is programmable in Arduino and in CircuitPython, as well as MakeCode and a couple of others as well. This thing's pretty universal. Actually does a lot for the what's here. But anyways, those are all options. But we're going to start with the Arduino version. So we're going to do that now, and I'm going to just move these other ones out of the way for now. We're going to fix that one up, and like I say, we're going to do some tweaking on that one later. I'll move these other 2 processor boards right out of my way. And what I'm left with is this setup here. So there's my Arduino, and there's my little level control right here. So we're going to show you how all of this works. But in order to do that, let me go to my main page, and I want to show you how this thing is wired up, and also what we're actually trying to accomplish with this today. So over here we have this, and I'm going to start out by just showing you what we're going to connect. Actually, let's talk about what we're going to do. What I'm talking about here is I can create this track level indicator, and the biggest part we have, one of the biggest hassles we have when we're doing modules is getting them level. We don't want them really running downhill. We don't want the trains running uphill. We can handle a very slight angle, so not quite perfectly level, but we don't want a lot of angle, because when we're going in a loop and we're joining a bunch of modules together, if we're not level, by the time we get all the way around, we'll find ourselves that the tracks don't line up anymore. So you want to start out basically level and stay there the whole way around. Does it have to be perfect? No, but it has to be close. And really, that's what this whole point of this thing is. Now, this particular sensor is just mounted on a big heavy bar. I'm going to zoom this in as well. Let's see if we can zoom this in a little bit. Looks like I might lose it. I can bring the bar off to the side, I guess. Let's see if we can't bring everything in here. There we go. And what I've done here is I've just used some double-sided tape on the bottom of this sensor. There it is there, double-sided tape, and I've just stuck it to the side of this bar. And this is a bar of key stock. Key stock is a very hard steel material, and actually what happens with it is that it doesn't tend to warp or bend over time. It's pretty tough. It's a pretty tough material, so it stays pretty flat, and it's a very high tolerance from side to side. So this happens to be very square. And I think this is like a 5/16 or 3/8 piece of square stock. And this would work. I would suggest building a little different. I would mount my sensor. I would actually mount all of my components, and that's the reason why you might want to consider using something like the trinket, because the trinket is very small. It's actually slightly smaller than the sensor board. You could wire all these together with the batteries and some LEDs, and you could have the whole thing working and mount it on your own frame, whether it's a block of wood, a piece of plastic that you've 3D printed, or something else that you've mounted it to, and you could actually make it so it fits on your tracks. So you could use it in N scale and have it fit right on the rails itself and sit on them. You could do it in HO, you could do it in O scale, ON30, S scale, whatever you wanted. And you can make it up in any length. I wouldn't suggest anything more than about 5 or 6 inches long, because you want to sit it on one piece of track that's relatively flat. And then what you do is you go from there and you work your way around the layout. So let's have an idea of what we're actually trying to make this thing do electronically. We're always talking about these things with angles. And we talk about two different things. We talk about angles in degrees, and that's how far off of zero we are for level. But we also see something else that's used in our daily lives. When you drive, or when you have a model railroad, they often talk about grades. And grades are a little bit different. So let's have a look at what they're talking about when they're talking about grades. So what I'm going to start you out with here is I'm going to start you out with a site. And this is a site that I looked up and I found on searching through Google, and this is called the Engineering Toolbox. And if you're looking for an address for it, I'm going to put that up on the page too, so it shows up here. And it's going to scroll across the bottom, but basically it's just https://www. So you can just type in engineeringtoolbox.com, and then to find this page, I found this page is a bit of a pain to try to find within their list. So it's slope-degrees gradient grade d underscore 1562.html. Now I'm going to let that scroll so you can actually write that down or come back and refer to this later if you want. This takes you to this page here, which they call a slope, degree, gradient, and grade converter. I actually found this pretty neat, so I'm going to scroll through a little bit of things of what they do in there. So first of all, they talk about what are we trying to do when we're measuring grade or angles and this kind of thing. And basically, you're taking two measurements. You're taking the rise, and you're taking the rise and the distance, and that's going to create you the slope. So the grade is just the height divided by the length. So if you have a height of 1 and a length of 1, your grade would be 1 divided by 1, which equals a grade of 1. And you can carry on, and if you did that, actually it's not a grade of 1. There's a little bit more involved. But this is just slope in degree radians, they call this. Actually, when I moved my mouse over it, it was there, and now it's gone. Let's see if I can get it back. So let's look at the different ways of measuring using these particular things. Because there's a grade, there's the new length, and this is just a hypotenuse triangle. You can do x squared plus y squared equals L squared, and you could do the math for that if you really want to. But this has got a tool on here that helps you. So first of all, we can do it expressed as an angle. And there's a math formula here, and basically this is here, it's the slope of the angle is equal to the tangent, the inverse tangent of y divided by x. And if you figure that all out, it comes up with a nice thing in angle, and it goes from 0 to 90, as long as you don't go past. If you go past, then it's changes. And then it says slope as angle, and it comes out with it, and here it is here. He used an example of 1 meter by 2 meters, so 1 meter up, 2 meters across, comes out to 26.6 degrees. Then you can do that as a grade, and the grade is just simply, the grade is equal to the percentage, so 100, times y over x. So if you do that, and you do that formula, you end up with a 1 over 2 is a 50% grade. Pretty straightforward, that's a 50% grade. In my other example where I used 1 over 1, that would be 100% grade. So the rise is equal to the run. And then you've got this pitch, and you go through, and then they go into roof pitch and slope, and they get into all the different things. But this is the tool I love on this page. And this works out really good because I can come in here and I can actually start doing this. And what it does, I put in what's my rise and what's my run. So if I have a rise of 5 inches and my run is 100 inches, this is a very practical solution. I'll calculate that now. And it tells me I have a slope in degrees of 2.86, or in percentage, it's a 5% grade. So when we talk about it, I use a 5% grade on my train layout down below in my house here. And I have a 5% grade on there, which means I have a rise basically equal to this. For every 100 inches of horizontal travel, I actually rise up 5 inches. So I actually gain altitude of 5 inches. And in my case, I've got to go about 18 inches. So I actually have to go, if I wanted to figure it out what it would be, I could do this. Let's say it's going to be, okay, I want a rise of 18 inches. I want to have a run. I know it's going to be over 300. So let's say I pick 300 and, well, let's start with 300. And I calculate that. I find out that, whoa, I'm actually at a 6% grade. I'm too steep. I need a longer distance. So I can come in here and say, well, I need to run then for 330 inches. And if I calculate that, I'm down to 5.45. So, okay, I'm getting closer. So let's double that to let's go up to 360. There's my 5% grade. So 18 over 360 is a 5% grade. So that means for me to get from my lower level of my train layout to my upper level, I need 360 inches of horizontal running space to get that high. And if you divide that by 12 and the whole bit, you figure out how many feet that is to get around. And in my room, that works out to a fair distance around my room. I actually go through a staging area, but I can rise that 18 inches. So this is how I can calculate that. It's a very practical solution to figure out what's going on. It also gives me one more thing on here that I don't normally get. It tells me how much distance I need. So if this was a straight run, I actually need more than 360 inches of track. I actually need 360.45 so inches of track. I use slightly more track than what the run was because my angle is fairly small. So I'm at my 2.86% or degrees, which is 5% grade. And it gives me a slope. That would be a pitch of 0.6 if this was a roof. And it gives me a length of 360.45. Since I used inches to do my calculations, this would also be in inches. So there's a very handy tool for you. That is a fantastic tool. like I said, you can copy down that. You can play this video back, freeze it, get that engineering toolbox. I grabbed that and cut and pasted it right into this page here. So that's the actual page that's up here at the top of the page, which is really hard to see because it's small, but it's definitely a lot bigger down here for you. So that's what we're building. I want to know if this is an angle. I want to know when I'm flat though. But this is what we talk about with slopes and grades. All right, so let's turn those off. Let's hide that information. And let's move into what we're doing here. So the first thing we're going to do with this is we're going to look at the wiring for the Arduino. So let's see what we hooked up and what we're using. So I'm going to show you this here. This is my fritzing diagram. Here's my board. Now, when we look at my board, you'll see there's a plug in the end of it. I have a cable that actually allows me not to have to use the pinholes that are on here. These are the pinholes that are already built onto it. Basically what it is, it's the input voltage, it's the ground, and it's the SCL and the SDA pins, which are the I2C communications that are connected back to the board. And it's pretty simple. It's just power, ground, and this will take 5 volts or 3 volts, so it doesn't matter which board you're using. The same interface board will work with both. In fact, we're going to take this same board and we're going to move it on to the CircuitPython version later. And it's just a communication line, and that brings in everything that's inside of this thing, which is actually more. It does way more than what we're going to use it for. Externally, I've hooked up 3 LEDs, and basically what I've done is I've hooked up a green LED in the middle, and I have a red LED on each side of it to tell me if I'm level or not. And I have 470 ohm resistors, and these are just connected to pins 12, 11, and 10. And then I have them connected to ground on the other side to complete the circuit. So I can set my level indicator, so I don't need to know numbers when I'm actually using this. It just gives me 3 lights to tell me, am I level or which end is high? And that's basically what it's going to do. And the idea is when I level this, I'm going to have just the green light on. That's what the idea of it. If it's level enough, and you set your own tolerances inside the program, when it's level enough, you say, okay, I'm done, let's carry on. And that's what we're going to do, and that's how we level up a module really quick. We place this level that we've built with the indicator lights, we put it on the track that we want, and depending on which way the lights are lit up, you go up or down and until you're level. As simple as that. So let's have a look at the program now. So here it is here. Here's our board. Right now I'm showing off level. If I actually raise this a bit, because I haven't calibrated this one, I can actually see I get just the green light. If I lower it just a tiny little bit, it's on there. I can actually get to a point where 2 lights can come on. So in this case here, if I have 2 lights on, it's telling me I'm really close to being level. I move it up slightly, the red light shuts off, the green light stays on. I continue to raise this up, now the other red light comes on, and eventually the green light goes out. So I can do that just by changing the angles by lifting and dropping this board. I can actually cycle through those lights, so I can tell when I'm level. Now, I haven't calibrated this. It's pretty sensitive, and you should calibrate this, or you just adjust your program accordingly, because every time you get one of these boards, don't forget that little sensor in the center of that board there is actually soldered in place. And that means that it could be slightly higher on one side than it is on the other because of the thickness of the solder when they solder it on. And if that happens, even the smallest amount off level is going to throw this thing so it's not level when you start. So you calibrate it on a known level. You put it on a level and then you can calibrate it. So let's have a look at what we did to build this program. And again, I have over here on the right hand side of the screen, I have the basic program. So the first thing I'm going to do, I'm going to go File, Save As, just like we always would. So I'm going to save as, and I'm not going to save it in my Arduino folder. I'm actually going to save it in my electronics show folder. We're way down here to the level. This is episode 21. I actually have one in already built here, which is what I know how it works. But I'm going to create a new file in here, and I'm going to call it, now this is level test live. So here's our live version of what we're doing today, and it's called level test live. So first things I always like to do is I always like to put a title in at the top. So I'm just going to go in here, level test live, and I like to put in the author so I know who to go back to if I have questions. And I am going to put in here something in here just as a reminder. This is a original code. It's from Adafruit examples. So I've actually used some examples of theirs to help me build. That's a better way to spell it, and I guess I can use a small e in here. Adafruit examples. Now the reason I like to put that in there is because I am using some of their code. Now they allow their code to be used by all means. I'm just giving them some credit where credit is due, because without their helper files it would make it that much tougher to write one. So the next thing we do is we include any helper files, and we are going to include some helper files, so we're going to talk about that. So include helper files. And I'm just going to copy them over because there's 3 of them that we need. Copy, and I'm just going to go in here and paste. And I'm going to tell you that right here, this is one of the things I found out is I need the Adafruit LSM 303 Excel.h, because that's the actual chip that's on that board. So that tells it how to do it, and then an Adafruit sensor is part of their communication package. So it uses these 2 helper files to fully talk to that board. And then wire.h is nothing more than my I2C communication setup. So that's going to be what I need to do. The next thing I need to do is I need to create an object. And if you're wondering how I found out that I need those helper files, is basically I went to the Adafruit site where I purchased that board, and in there they have a link to their learn files, and in their learn files it tells you you need to install these files, and here's the example code. And they give you some help with that. They're actually really good about building files like that for you when you buy one of their sensors. So this is create the acceleration object. And something that they do here, which I guess they need, is we're going to have to create it with ID. We're going to have to create an ID code to go with it. And that's fine. That's just something they ask us to do, so we'll do it. So I'm going to copy that line of code in because it's fairly long. I'm going to paste it in here, and like I said, it's fairly long. So what they've done here is they've said this is the Adafruit LSM 303 Acceleration Unified, which is all part of that file. Excel is the object, and it's going to be connected to Adafruit Unified, and it's going to be given ID number 54321, which was the default number they gave it, and I didn't see any reason to change it. You can change it because you can have more than one of these as well. So that's what's happened there. Now I'm also I would normally create some variables here, so I'm going to leave a spot for that because we're going to have to do that to add the green lights. So what we're going to do is we're going to go in here and we're going to go create any assignments and variables. So when we go to hook up these LEDs, we're going to need to assign pins for the LEDs, and we're going to have to actually give us another value. I need one other value to help run the program here. So this is just something that we're going to do, and we're going to have to add those later, so I'm leaving a spot for it. The next thing they're going to do, and this is something that just Adafruit has done on its own, and in fact we don't actually need it, but I am going to set it up. And it's a fairly long routine. This is right out of their helper file. And I'll explain what's going on here, because it's going to go in right here. And it looks long. What this is a subroutine used during the void setup. So during setup, we're going to call this routine up. We're going to call something called display sensor details, and it's basically it's a subroutine, but it's tied to the void. It's tied in a little bit different, and it's sensor underscore T sensor, which is something that they have set up for theirs. Excel.get sensor is a keyword and sensor, so it's going to bring in all the sensor data, and what it's doing is bringing in a bunch of stats. So what we have going on here, the first thing it's going to bring in is the name. It's going to bring in the name of the sensor, and we're going to see how that works because we're going to run that and we're going to see how it works. And it's also going to bring in the version. It's going to bring in on the ID number. That ID number should be that ID number that we created in the object. So that'll be 54321. Then we're going to have our maximum value and our sensor maximum value. We're going to have our sensor minimum value. We're going to have a resolution setting, and we're going to have the sensor resolution. It's actually going to tell us what it is. And when we're all done, it's going to delay for half a second, and then it's going to move on from there. So that's just something that they're going to do, and it's going to give us some information. Now, this is connected to the serial print, so you're only going to see this in the monitor. If you hook this up without the computer connected, it just doesn't. It tries to send it, but there's nowhere to send it, and it just continues on. So now what we end up doing here is we actually end up going into the void setup. So we're going to go down here, and I'm going to go in here, and if you notice, there's going to be one little difference here. Because I grabbed a setup file from up above, I'm going to add that word in here. This is something we don't usually see, but I'm going to add the word void back in here. And what void does is it links it to that file right above it, that subroutine. So normally we don't bring them in that way, but that's the way they decided to bring it in. There's other ways we could do it, but I'm going to leave their example, and I'm not going to try to destroy it at all. It does work, and it seems to work well. So the first things I'm going to do in here is I'm going to set up the serial monitor. So let me do that. So I'm going to go set up the serial monitor. So this is something we've done many a times here. So this is just serial.begin, and we give it the baud rate. So we're just going to choose 9600 because we're used to that. So there's our serial begin. And then what we're going to do is we're going to send some information to the monitor. So I'm going to grab a couple of lines here just to save myself a little bit of typing. And what I'm going to do is I'm going to print in here accelerometer test and a blank line. That's really all that is. It's just nothing more than a blank line. Now, there's something that they add in here, which I've seen done quite a bit. And what we have to do is we have to start the sensor. So, pardon me there, I had to clear my throat. What happens here is when we start one of these programs, we have to start the serial begin. Well, we have to turn on the sensor as well, and we've done this lots of times. What they do is they build in a correction for it. So I'm going to go copy, and I'm going to go paste in here, and I'll explain what they've done. And this is done. We could just put in excel.begin, bracket, semicolon, and be done with it. But what they've done here is if not begin, so if it hasn't started, it says here, hey, and the other part of start was all this information up here. It actually started on its own. So down here it says here, display an error if not seen. And basically what it says here, oops, no LSM303 detected, check your wiring. So if you forgot to connect it, this would do it. And it says while one, which is true. So as long as this is true, this stays and doesn't go anywhere, and it just stays up on the serial monitor. When you connect it and it starts, it then bypasses this section. So that's what that does for us. So it actually works really well. It's just something we may not be used to seeing all the time. Then what I want to do is I want to display some of my current settings. So I'm going to put in here display, whoops. Let's try doing it without all the backspacing and all that. Display current sensor info. So what this is going to do, it's going to give me a detailed account now of what's going on in here. So what I want to do is I just want to grab a nice little statement. I'm going to copy that. And it's just display sensor details. That's all I'm doing, is I'm just getting all that information. And I just want to make sure we have it before we go into our main loop. And then what I can do down here is I can actually go down here and I'm going to give it a whole bunch of serial print commands again. And let's see here. I got to go all the way back up to here. There's a lot of overhead in this one that's right out of the example. Like you can eliminate most of this if you really want in your own code. So we're going to throw this information in here. And what it does, it sets the range of the sensor from 2 to 16 G. Now that's G-force. So G-force is basically gravitational pull, but what it is G-force is on you, is if you're standing still, the G-force on you is 0 horizontally. And the only G-forces on you is gravity pulling you down to the earth. So that's your G-force, which is really minimal. When you move forward, when you start to accelerate, your body wants to fall backwards. If you're sitting in a car, you get pushed into the seat when the car accelerates. That's a G-force that's being pressed on you because you have to catch up to the car since you're sitting in it. And that's the force of the car pushing you until you're at the same speed, then you're relaxed again. When you stop, you get negative G-forces because all of a sudden you're trying to go forward and the car isn't, and your seat belts are going to help restrain you, or your muscles are, whatever the case may be, but it's going to help keep you in that seat so you don't hit the windshield if you're in the front of the car. And this one has an adjustable range from 2 to 16 G. So this thing can actually handle up a fair bit of force if you want to set it up to that kind of range. It'll actually, the chip itself will handle quite a bit. What we've done is here, we've set the range to 2G. We've gone to the smallest setting because we want the most out of it that we can get. So it says here, set range 2. And then what we've done is it's going to say, hey, based on whether we chose 2G, 4G, 8G, or 16G, it's going to print out that statement. And this is switch case that I showed you last week. So it's going to say switch new range. New range is equal to whatever we set it to up here. And what it's going to do is it's going to say, hey, you want to find out what this is, then come down here, and if the case is equal to 2G, then print this message. If it's 4G, print this message, and so on. That's all that is. So that's the G settings for the chip. The chip also has another ability for setting up the resolution mode of it. And this will affect a couple of things here. So let's set it up and then show you what the variations can be. There's a lot to set up on these chips, which is not uncommon with these things. But now we can set up the resolution of the sensor. Luckily, we only have to do this once when we start it up. Once we start it up, it's going to stay there. So what's going to happen here is we're going to have the resolution. So you're going to set it, and I set it for high resolution. By default in the original code, it said normal. But I wanted to go to high resolution because I got more accuracy out of it for my purposes. And set mode 2, and it's the same thing again. You have what they call normal mode. You have a low power mode, which is not going to take a reading as often. So if you're running off of something like a button battery or a very small battery, you could actually run it on low power, which means it's not going to check as often. Or you can run it in high resolution mode to get the most detail out of the information you can. But it's also going to use more power because it's constantly reading the chip. That's what I chose, was high resolution. That's what we want for this particular one here. And then what we're going to do is we're going to come down through here. And I'm not 100% sure. We might even try a little test before we're done here. They put the word void back inside the loop void. And this is everything here. Yep. Oh, I know why they did it, because they're addressing the chip. So what I'm going to do here is I'm going to grab their code that they had in here, and I'm going to throw it in. Now, I put in my own code for the latter part of it, for the lights and that, and I will show you how that works. So let me just grab theirs. So get a new sensor event. So they're creating the event for sensor. It was the same as what was done in the original loop up top. They've created that event. And then what they've done in here is they're going to print the results up on the serial monitor. And we're going to see how that works, because we want to see how these numbers come up and get a better idea of what's going on here. And then the last thing we need to do is we need to create a slight delay. Otherwise, we're going to have information scrolling by so fast on the serial monitor we'll never be able to read it. And to do that, we just come down here very simply, and we're going to throw in a delay. This is nothing more. So we're going to create a slight delay, and in this case here, I created a delay of a half a second. So every half a second, we're going to update this information. So let me check to make sure that I am connected. According to this, I am connected to my Arduino Uno. Let's validate this to make sure I didn't forget anything when I'm copying it over, because that can happen. So it's compiling the sketch. If it works out okay, what I'm going to do is I'm actually going to download it into this particular one. I'm going to overwrite what's in there. Semicolon. Missed the semicolon at the end. That's why we validate before I try to load. And I can see I did not highlight it when I was copying. So let's try that again. It should compile fine this time. It's always nice when we can find our mistakes quite easily. Usually you go to the yellow bar, the orange bar where it tells you the problem is, and look at something just prior to that, because something didn't finish properly when it was checking. And this time it says done compiling. So let's go ahead and load this up. I'm going to go ahead and load that up. So it's going to go through and compile again, although it should be a little quicker this time. And there it goes. It's compiling. And now it's uploading, so it's actually updating the chip right now. You can actually see the two lights on the chip were on the serial parts, and now the transmit light is on because it's sending back information. So let's open up the serial monitor. So I'm going to do that. And what I'm going to do is I'm going to bring that back over so you can see it. Put it on the page there. And what's happening here is we're seeing there's the X information, the Y information, and the Z information. And it tells you how many M's per second squared is the amount of force that's on it. So what I'm going to do is I'm going to lift this end slightly. By here, we'll see the X drops into the negatives. We're going to see that when we bring it down here, we get closer to 0. 0 is right about, it's hard to get exact. It's pretty finicky. There's 0. I had it for a moment. And if I let it sit, I can actually tilt it the other way, and we can still see that the numbers get larger. So when I lift this end, the far end, the top of it, the numbers go positive. When I lift the end closest to the bottom of the screen, this end, the numbers go negative. So we can see that we can go off center. So it's actually measuring the fact that we're level or not. Ideally, level is 0. And as you can see, just sitting there, it's also getting some various readings. It changes from about 17 to 20. Seems to be about the range. I saw 21 go by there, but that's about the range. Let me just clear the data. What we're going to do is I'm going to repeat this. I'm just going to download it one more time, or upload it. So I'm going to let it compile because I want to show you the first part of the data. I'm going to clear that screen so you can see it. When it comes up, remember it said it printed all this information at the top. Let's go through what that is. So I'm just doing that again to show you all those sensor settings and everything that it likes to do. And then I'm going to turn off the auto scroll so I can freeze it up here and look at it. So first of all, it came up with accelerator test, which I had in my code. Sensor is the LSM303. It's driver version 1. There's that code. So if you change that ID code back up in that line in the early part when we created the object, you get your ID code up there. It's going to tell you what the maximum values are, minimum values are, and the resolution. And then it says set resolution to 2G, and it's set to high resolution, and then we start getting the live data. And of course I put it back on auto scroll. It picks up whatever data. And every half a second we're getting in new data. So it's working. It's doing what it wants to do. So now let's move on to the next part here. So that all works, and we know we get a rough indication of what's going on. Now what I'm going to do is I'm going to create some objects here. So what I'm going to do is I want to add my 3 LEDs. My 3 LEDs up here didn't do anything that whole time. When I'm doing this and raising and lowering it, I should be getting LEDs lighting up, and there's nothing lighting up. So let's create those objects. So I'm going to go up here and I'm just looking at my notes. So here, create any assignments and variables. This is where we wanted to add that stuff here. So I'm going to create some. So I'm going to create an integer for the LED red 1 pin. And so that's the first pin, and I'm going to make that equal to assignment number 10. So it's going to go to pin 10. I'm going to create the green pin that goes in the middle now. So it's LED green pin, and I only have one of those, so I don't have to bother numbering it. And that's going to go to pin 11. And then I'm going to create the third LED, so that's LED red 2 pin. So that's what I've done here, and I'm going to set that to pin 12. Now I am going to add one more value in here because I want to use this, and I'll explain what it is when we do our calculation on how to make the lights work. I'm going to put in here float. So I'm creating a number that has a decimal place in it. If you notice when we had up our serial monitor, okay, so if I pull up that serial monitor again, you'll see these have decimal places in them. So we're going to want to use those decimal places. So we can't use an integer. An integer does not have any decimals. So we got to remember that when we're doing this. So what we're going to do is we're going to create a floating type number, and we're going to call this one, since we're doing the X scale, we're going to do X value. And I'm going to make that equal to, so that it knows that we know that we created it that way. I'm going to create it with a decimal. So there's my 4 variables that I need to make this work. So very quickly, I created 3 pins, and I created everything else that I need in there. 3 pins and 1 variable that is going to be used for some math. So let's go down here to our setup. Here's our void setup. I'm going to just go in front of this here, and what I'm going to do is I'm going to create, I got to set up the LED pins. So this is our normal, this is pin mode. This is our normal one that we use, and I'm going to make this one LED red 1 pin. That should be familiar from up top, and I'm going to set it as an output. And then what I'm going to do is I'm going to highlight all that. I'm going to go copy, Control C, go to the end, hit enter, and I'm going to paste it twice more, because what I'm going to do is I'm going to change red 1 to green, and I'm going to change red 1 to red 2. And I now have my 3 objects for my 3 output pins. So that's a nice simple way of doing it, nice and quick. We get our output pins working. Now down here in the main program, before the delay, after we do the readings, I'll let them go ahead and do their thing. I'm going to go in here and I'm going to throw in some of our own math. And I'm going to make my life easy because I've already created the math, and then I'm going to explain it in detail. It's not really that hard, but it's something that we're going to do. So this is what I've created in here. So I've created this block of math, and it says control the LED states based on X value, and that's exactly what I'm doing. And what I say is X value is equal to event.acceleration.x. So I'm actually reading just the X value. I'm not worrying about the Y or the Z, so I'm just measuring it along the length, the vertical length here. I'm measuring along here, this length. So I'm doing that. And if the X value is greater than 0.10, turn on the red LED, LED 1. If it's otherwise, so in other words, if it's less than 0.10, turn it off. Simple. The other red LED, if it's less than negative 0.10, then what do I want to do? I want to turn on the other red LED pin. And then if it's not less than that, turn the LED off. And then this is the big important part here. What I have here is I have if the value is less than 0.15, and it's also greater than negative 0.15, turn on the green LED. So if I'm getting close, I want to turn on that green LED. And if it's not, we'll turn it off. But what's the big difference here is I actually have an overlap in my distances. So if the distance is 0.11, this red LED would come on. But so would this green, because it would fit within this range. So what that does, it tells me by having two LEDs on is that I'm close to level. And then what I've done is I've actually made my life easier. So I'm going to go ahead and I'm going to upload this, and we're going to see this work. And I'm going to open up the monitor again so you can see it when it loads up. You'll see the data come by. Now you can see the data scrolling by over here on the page. So right now we're outside of that 0.15, so the green LED cannot come on. So let me just rise that up just a little bit. There it is. I have a green LED on. I'm going to lower it a bit and see if I can get there in between. And sure enough, when I'm in between, I get a red and a green coming on the board at the same time. And then if I go too far the other way, I get into the negatives, I can see the other red comes on. So very slight movement gives me my ability. What I want to get to is I want to get to the point where I have just the green on. Now I talked about calibration. There's a couple things you can do for calibrating. When you're mounting this, make this board adjustable so it's like a hinge where you can rise and lower it. Maybe use shims on one side. Shim it up on one side when you screw it down to your block. It's got 4 mounting holes on it, which is really handy. And then when you're screwing it down, put little shims in here until the board sits level on a known surface. And once you've done that, you're done. So that's a mechanical calibration, if you want to do a mechanical calibration to this thing. And once you've created it, you should be good forever. And as long as you do that, you're good. So I can actually, actually have to press down on here. I can get it to go, because the pad is soft, I'm able to get it within there. But you can see we can adjust it now, and we can play with it, and we can get readings that are reasonable for us. So we can actually get some really good readings on here. We can create a mechanical level in here. We can actually get those 3 indicators. And just by using 3 simple lights is a lot easier than trying to get up and look at a bubble level. For years and years on our layouts, we used to put on anything from a 6-inch level to a 2-foot long level on our module, trying to make it level. And somebody would be adjusting the feet and somebody else would be watching the bubble. If you put this on there, you can adjust the feet, look up, and depending on which way your lights are, it tells you which foot you need to adjust. Pretty simple. And I hope that makes that part of it simple for you, because that's really what we're doing. So I'm going to go ahead and close this part down. We're going to switch over to the CircuitPython version because it works a little bit differently. It's almost identical, which they usually are in these two. It's just I can make changes faster there. And we're going to see if we can do an electrical calibration on it really quick. So let me just turn off the Arduino window. So the Arduino code is, I got so many things on here today. Should be this one. And now I want to turn on the next one. What am I? I'm missing something here. My Arduino code. Ah, there it is. Arduino off. And there's our other code. So let me change out the board here. So all I'm going to do is I'm going to unplug these leads because I'm going to use the same board. And I'm going to move this out of the way. I'm going to bring this one in. And in here, I need yellow on this end pin here, which is actually that one. I need the blue pin, the blue wire connected to the one beside it. And I got to get my red and my black untangled from everything. And they just connect over to the far side of the board. We'll be focused back here in a moment. And we'll let it focus back up. Like maybe I can get it this way this time. Oh, this is a little bit. There we go. So, have 3 LEDs up there, and I've got this down here. And right now, it's not happy. So basically what I'm going to do is I'm going to go up to my program here. I'm going to open up my serial window. It's got a problem when it was loading because the I2C was missing. I'm going to go ahead and just hit save. And when I do, it comes back to green. Uh-oh. Did I hook up those two backwards? Or did I miss my pins? Let's have a look at our drawing. Let's go and make sure we're doing this right. So up here, we'll go to photos. And let's go to our photo and make sure we connected this right. Blue, yellow, okay, black and red. It's still not happy, but we'll figure that out in a moment. Okay. So what I'm going to do here is I'm going to hit save again. And it says it's not there. Why does it say it's not there? Maybe it needs to be powered down and powered up. So being such a pain in the butt program sometimes, what I'm going to do is I'm just going to, I only wanted to have it because I thought I'd have it powered up from the start. So what I'm going to do is I'm going to eject that. So now it tells me it's safe to remove. I'm going to unplug it and plug it back in. And when I plug it back in here, we're going to come back up here. We're going to hit save. That's my window. Huh. Wouldn't you like it? All these little simple problems and something's not happy. That's what I get for unplugging it and plugging it back in. Under load, I guess. Did I reverse my black and my red? No, I have a green LED on the board. That's a good thing. There's a little green LED on the board. Let's unplug that connector from there. Plug it back in. And if I go up here and hit, I'm going to close the serial window and reopen it so I get a fresh window. And the bad is the board for that. Isn't this nice? Isn't this nice when things don't like to work for you on this day? And it was working before. I can get rid of that window. I can lower that down. I2C device. Everything should be there. It doesn't like something I'm doing. It should be going to the right spot. No device at 19. Okay, well, you know what? We're just going to look at the program then. Unfortunately, it's being stubborn right at the moment. And I don't know how much time we got to troubleshoot it. But we should have had no problem with this. And I'm not sure why. I'm going to try ejecting it once more. I'm going to go through a couple of steps here that sometimes we end up having to do with these things. So I'm going to go eject that. So now it's gone off the list. I'm going to unplug it, which you'll see the lights will all go off on the board. Let it settle out. I'm actually going to close Mu for a moment. We'll reopen that. I'm going to plug in my board again. Did I actually have these two colors reversed? Wouldn't that be a shame if that's all it is? So, it's there. Let me just go open up Mu again and we'll have a look. It'll recognize there's a board there. We'll get that over. And what I'm going to do is I'm going to open up my serial and I'm going to hit save. And it's working. You know what? I had those two wires reversed. Okay? Oh, you gotta love I squared C. It depends really well. So that's what happens when I was doing my drawing, because I didn't actually have it hooked up to the board. So looking at my drawing, you just gotta make sure you hook up SCL and SDA to the proper pins. It's really picky that way. Imagine that. Okay, so there we go. We're up and running though. So up here we have it, and we can see the X, Y, X, Z angle, which is what I'm dealing with, is dealing with how many degrees movement there are. So what I've done here is I've gone in here and I've gotten all this stuff working, and let's walk through the program. So let me close up the serial monitor just so we can see. So this is my track level indicator. So my helper files this time, I have time coming in. I also have from math import a tangent to and degrees. So I'm going to tell you, this is something we didn't do in the other one, but this is something I'm doing in here. Board, digital I/O, bus I/O. Bus I/O is nothing more than I squared C, and then of course the accelerator file itself, the LSM 303 ACCEL. Now, we're going to set up the communications just like we always do up in here. So we're going to have the I squared C bus connected. We're going to connect it to the default connections on the board, and then we're going to create the object for the acceleration, which is just the big long name of the accelerator. We're going to call it sensor is the object name, and it's connected to I squared C. Here's all my LEDs. So I've created them to pins 10, 11, and 12 like I did on the other one. And I've just set them as output pins. So there's all my setup for there. Now there's a couple of subroutines here that run at the beginning. One is to set up the vector in degrees. Remember I talked about tangent? If we look back at that, the Engineering Toolbox that I showed you at the beginning of this stream, what you'll find is that they had the tangent was part of the formula for doing y over x, and it gave you the angle and it returns an angle. And that angle actually got used to create how many degrees of movement it is. So they're actually measuring in degrees in this one. So when we go through our loop, and this is our loop, you notice I don't have all that other setup information. There are things for setting the resolution and things like that in here. I just haven't gotten into those detail settings, but they're available to us. What we can have in here is, while true, get the calculated angle from the sensor. So here it is. It grabs it and it prints it as XZ angle equals, and then the format is 6 digits, 2 of them being decimal places to 2 decimal places in degrees. And then there's the format. And what I've done is I've actually brought in the value and I've subtracted 90 from it. Because as it was laying horizontally here, it showed me it being at 90 degrees. And I said, no, I want that to read 0, because I prefer to read plus and minus 0. So that's what I did, is I've changed it and I put in a little math that says, read me the value at 0 instead of at 90. So if I open up that serial monitor, we'll see those numbers. It tells me at how many degrees there are. And if you remember from the Engineering Toolbox, we actually could relate degrees. Now 2.86 degrees, I believe, was 5%. So I can actually go into here and get my degrees down really small. And then what I can do is I can raise this up. And if I were to raise this till too far, 2.86, somewhere close. There's 2.8. 2.75, you can see I can get to a 5% grade on this thing. So I could actually read the grade on here if I did the rest of the math and figured it out. Now, what's happening here with my lights is a similar story to what I had before. So my lights, I have one that tells me where it's high, so it's high at this end. So I need to raise this end in order to bring it towards level. And you can see on my transition, I get both lights picking up, just like I did before. And then going up, and I go the other way until I eventually just have that light on. But the green will come on as I get close, just the green, and then I can have green and red. But we can see here that we're actually off by about, it looks like about a 1.3 degrees maybe, about 1.3 is on normal. There's a little bit of vibration even in the table. This thing picks that up. It's very, very sensitive. And we might actually want to decrease the sensitivity a little bit. But this is very, very sensitive to movement. So you might have times when you're flickering the other lights, and that's okay. As long as green is on steady. That's our big thing. So down here, what I've done, let me just reduce this a little bit. Get a little more room. Once I printed that out, what I've done is I said, hey, if the angle is greater than 90.4, do this. If the angle, so I'm using that 90 degrees again. If the angle is 89, less than 89.6, make this one true. And again, I have the false statement. And finally, the green light, if it's, and I've done an overlap again. So this was 89.6, I've used 89.3 and 90.7 instead of 90.4. So I've created about a 0.3 degree overlap in each direction, since this is measured in degrees. The other one was just a unit of value, which was being measured differently. This is actually measuring actual degrees. So I can come down here, and then what I do is I do this, and I have my time going by pretty fast. It's at 0.25 seconds. This is one of the beauties of this. Let's say, hey, you know what? That's too fast. I want to go to 0.5. I can save that now. It's already saved. And there you can see how fast the numbers are updating at the bottom of the screen. They're updating at a slower pace, which is fine. If we wanted to really prove this out, I can just change this to a 1, do it every second, save it, and you'll see these will just scroll by nice and slow now. So how often do you need to make your reading? You can set that up in the delay in CircuitPython, and that's a big advantage of CircuitPython. It's very quick to edit and get you up and running. Now I wanted to talk about correction, and I can do a correction electronically. I can see by default when I'm sitting there, I'm actually sitting about 1.2, 1.3 degrees out of whack, pretty close to 1.67, 1.17, 1.4, 1.6, just the normal vibration of things going on. So it's closer to 1 point, probably somewhere in the middle there at 1.2. But it's negative 1.2 degrees. So what I need to do is I need to add to angle XZ 1.2 degrees. I need to add that. So let's see if I can do that in the middle of the file here. So what I'm going to do is, after I've done the calculation, I'm going to change the value of angle XZ. So I'm going to go angle, better spell it right, angle underscore, and I'm not sure whether this is going to work exactly as I want, and I'm going to say it's equal to angle underscore XZ, so the same as what it was, and I'm going to say I need to add, because it's too low, I'm going to say add 1.20. So I'm going to change it just for this. What happens is when it reads the new value, it'll overwrite it and display the proper setting, but I'm going to get a modified version in here. So let me go to save. And now I can see I have a green light on my board at this level. So it's calibrated it very close. If I pick it up slightly now, I can see my red light came on pretty quick. Oh, there. So I'm really close to that. If I pick it up on this side, my red light picks up there. So I've actually got a pretty close calibration just by adding one little math statement and changing the value of it. If I do it before it displays, I can actually take this line and put it in another spot. So why don't I do this? I'm going to take this line now. I'm going to cut it out of there. And I'm going to put it after reading the sensor. I just moved it. So now it should even correct down here at the bottom. If I hit save, there's my new values coming up. So very quickly, I've done a self-calibration. And since all those numbers are positive, I can say, you know what? I'm adding a bit too much to it. I don't, oh, there's more, but I'm getting mostly positive numbers. You know what? So let's say this is a bit too much. I'm going to bring this down to 0.15, and I'm going to hit save. Look at that. That is really close to being 0. I get a couple of spots where it goes out, and that's okay. I'm going to get a light that flickers. Every once in a while, when I see my numbers go out, I might see a flicker on the lights. So there I've created a calibration because of the unevenness of my mount. I've corrected for it, or the unevenness of the chip being mounted on the board. So very, very quickly, I've done an electronic calculation just by making one little change. And I would comment that normally. So I would normally come in here and put in a little comment. This math calibrates the physical mounting. Okay, so something like that. So this math calibrates the physical mounting. So all I've done is I could go in and just change that one number anytime I want if for some reason it goes way out of whack. So there it is. It's corrected. So that was a nice, simple way. Could I do that in my other one? Sure. I just have to do it before it gets to the LED. I could do that in the Arduino program. I can do the same thing, and the value that I'm going to be checking against, which is in angle_XZ here, is you just make that fine adjustment in the Arduino program to do the same thing. So I hope this was helpful. I hope this was interesting for you. I see I have a few people watching. I've probably got Brian in there somewhere. I don't know who else is watching, but welcome to the live stream. I hope you've enjoyed this. This is something that's actually fairly easy to build. All of this can be built into another board, and if you want, don't forget you can build this. I'm going to zoom out for a moment here. You can build it onto the Adafruit little boards. You could build this onto a, if I can get it in here, an Arduino board, so you can put it on an Uno. You could add it to this little trinket, and you could put it on in either language, or you could add it on to something like this, and then the sensor's already built in a Circuit Playground Express. So all of these are options. That doesn't work very well. Let's try it like that. All of these are options on what you can do. You can add it to any of these boards that you want. Make your life easy. Like I said, I hope you've enjoyed this. I hope it's been interesting. You can go on to here. This is nothing more than an accelerometer. You can buy accelerometers from a number of sources. You get helper files if you get them from Adafruit. Other places, sometimes they'll have helper files. Sometimes there's generic helper files for them. You pick and choose what you want. There's also many different versions of this as well, these breakout boards. And enjoy. Play with it. Build yourself a simple little level indicator that you can use on a module. Mount it onto a solid block that now fits your railroad. And you can see that the precision doesn't have to be there because you can calibrate it after the fact, which is always great. So, again, this has been Microcontrollers with kingernorth, episode 21, track level indicator with CircuitPython and Arduino. Thank you for watching. Thank you in the future for those that haven't watched it yet that will. And you can also link with me at my Twitter account, which is @kingernorth on Twitter. Or you can make comments and watch other videos for other episodes at youtube.com/kingernorth. So I hope this has been educational. I hope it's been friendly. I hope it's been fun. And who knows, we may have all learned a little bit today. In other words, take care and enjoy your time. Be safe. Bye, everybody.